Welcome to the Valve Studio for January 30th, 2017. Today I'm going to be covering my transformer design code that I worked on for power transformers. I got this from a couple of examples that I found in all my readings. You know, I've read RDH4 and I've read a lot of different things, but I was looking for a really comprehensive example to see not only how to determine the turns ratio versus the flux density and that type of thing, but actually look at how the build process takes place for a transformer. So I'm going to cut over here to my screen capture. The two books I found, the first one was called Engineering a Transformer from Stancor Corporation, 1945. And if we come down here to this, half of this book is a description of how Stancor works as a corporation from a transformer perspective. It's a great historical reference. That it shows a lot of pictures of the manufacturing line and what it looked like when people were doing their work, you know, those types of things. This is a really good book to be reading if you want to get interested in transformers at all. And starting on page 84, in the PDF document, there is a design procedure for a power transformer. They talk about the various steps you need to go through, and then they give an example in the next couple pages here. And to talk about what kind of laminations they used and what kind of decisions they made in the iteration process. And then they have a design sheet down here, and this is what would actually go to manufacturing to actually make a transformer. So this is in one. This whole example here is in basically 2 pages. It's an explanation, and then it's 1 page for how it actually got designed. Okay. Then I found a better example. There's a book here by a gentleman named Robert Wolpert. He was a transformer design engineer in Los Angeles, and he wrote 2 books, actually. This one is his power transformer design book, and he has another one on audio transformers. We'll be covering that in future episodes here. If you go through here, he has a design procedure. I'm not going to go through this. I'll have links to the PDF in the show notes. I recommend that you go ahead and read this one. It's very easy to read. It's very understandable exactly what he's doing. He's got a 12-step or 13-step procedure where he goes, let me get up here to the design procedure starts in chapter 2. He first talks about, from looking at an ideal perspective, you know, just looking purely at turns ratio and voltage and current ratios that occur in a transformer. But that, in actuality, is there are losses in a transformer. There's copper losses, you know, V equals IR losses. There are also core losses. There's efficiencies. There's a lot of different little nuances that make it so straight turns ratio is not going to work right if you want to make an accurate design before you start the wind, which is what we try to do here. Okay, chapter 2 is a comprehensive example. Actually, it's not an example. This is a procedure that he's going through, and you can see that he has these steps outlined. These are steps 1 through 13. We get all the way through. We determine what the primary turns ratio is based on the flux density that we chose, what kind of core we need to pick, how many turns there needs to be on the primary and the secondary. We look at the copper losses, we look at the core losses, we make adjustments to all the turns, we figure out the overall length of the wire that's going to get put into a winding. That leads us to the resistance. The resistance leads us to the voltage drops from the no load to full load. And then finally we get down and he goes and determines the temperature rise in the transformer based on the core size and the lamination weights that you've actually chosen. So that's probably about 10 pages of explanation there. And then he goes into a design example where he wants to design a 115 volt primary with a 6.3 a 10 amp secondary. And he goes through all the exact same steps that he went through in his design procedure. And he gets all the way to the end, and he talks a lot about the build. And he talks about the build is how the layers of copper wire are going to be built onto the bobbin, which actually is the middle of the transformer. So you can kind of see what his design procedure is. And he gets all the way to the end. You know, his last step is to determine the temperature rise, and he figures out that as well. And then he goes in and then eventually shows you what a winding sheet looks like, which in the Stancor manual, the Stancor example, it's this procedural chart, but in the Wolpert example, he calls it a winding sheet. So this is what you'd actually send to manufacturing if you're going to get this made. All right, so I've taken all his design procedures, and I've made a 3 Python classes for this. There's 2. There's the winding class and the transformer class. And what you end up doing is you type in a little bit of Python code. We'll show that here in a minute. And then you build your transformer with the windings in the order that you want to wind them on there. And then you get a chance to actually modify all these parameters that he's iterating on. And you get to do a real design by manipulating all the parameters. And there's at the end of this in the Stancor manual, it tells you here down at the very bottom of this, there's a section in here where it tells you if your design doesn't fit, what you should do. The calculate for the second trial build, it says if it's too large or too small, one or more of the following can be changed. You can change the lamination size, you can change the stack height, you can change the flux density, the wire diameters, or the insulation thickness. You can change all that in my code as well. Let's go over and look at some examples of how this works. So I have Jupyter Notebook running, and I'm going to go ahead and restart the notebook, and I'm going to clear all the outputs. And I'm going to show you the notebook here. So the first thing up the top shows you the references. This is the Wolpert book I was talking about. This is the one you must read. Stancor is good from a historical standpoint, as well as another example that you could look at. There is like a college level textbook called Electronic Transformers and Circuits by Ruben Lee. This book is also over at this is over at tubebooks.org. This one gets into a lot more theory about how to determine losses and just do real design. We're not going to go into that here. And then I have a link here to go from flex lines to Tesla, which is not that difficult. So we're going to step through a couple of pages. In Wolpert design book, we took 10 pages to explain this. I'm going to go through this pretty quick. Here are those equations for with no losses. These are what you start with. And here's the equations with the losses. So there's this efficiency that has to deal with how efficient the core is and doing the transfer from the flux density and the flux leakage and that kind of thing. And Wolpert goes and takes gives a ballpark estimate of what that efficiency is. And so his are starting values. I don't know exactly how my process is going to work on the efficiency side as well as the core loss, but we can determine that in future segments. But we'll go with his gut feel for his design because this is what he did for his career. So we'll start from there and use his experience. There's also this thing called stacking factor. Oops. Stacking factor deals with the when you have laminations and you're going to press them together. If the laminations aren't really cut very well, the ends will have a little bit of cut or a little bit of burr on it, and they won't stack very well. So he talks about stacking factor for both interleaving as well as a butt stack. And then here's the first equation that you end up coming up with. This is calculates the number of turns based on the voltage of the primary, and this constant down here is for sine wave power. Flux density is B. This A is the effective area of the core, and the frequency itself is the line frequency that we're working with. So you can change that here in the code as well. It defaults to 60 hertz for the United States. And there's a loss factor that he calculates in so that I did it again. There's a loss factor that he calculates in to determine the secondary turns, and then he determines the temperature rise based on the total loss that occurs that's been calculated based on the weight, and there's a little equation here that he goes through. And then you go, and the last thing you do is look at the percentage of regulation, which is no load to full load, what the voltage change is actually there. But ultimately, when you're going to design your power transformer for your tube amplifier, you already know all the currents involved on the secondaries. And so you basically are going to load up your transformer really close to where it's full load, and so you can sit right on the right voltage and not have a voltage fluctuation. So it goes in and it talks a little bit about the calculation steps that take place in the code itself. And if you were to step through the source code, there's a method in the transformer class called compute, and you can actually look and see what it's doing there. It does do a looping operation inside the code where it actually for the specific flux density that you're at, it loops through all the secondary turns to minimize the error between what you've specified you want it to be at full load versus what it actually computes out to be. Then it calculates the weights based on the laminations you've chosen. It adds a little bit extra for the bells and the brackets that you have. And then it calculates the temperature rise above ambient. Now, this is all done in C, Celsius. So here's some additional considerations. We'll be talking about this in a little bit, but the biggest consideration that you have is the choice of flux density. As the turns ratio is always going to be a division of two integers, because you're going to want to have complete turns on your bobbin, because you want the lead out wires to come out in a certain location on the bobbin. So you don't want to have fractional turns, and you want to have complete turns. And when you have a division of two integers, that makes the ratio of the primary voltage to the secondary voltage somewhat fixed to whatever the integer values end up being. When I first started working on this, I thought I could just put all these equations into a nonlinear solver and have Python's code figure out everything. But it turns out that being the iterative solver, by having to force your turns count to be integers, makes it so that it's kind of complicated, but the stepping algorithm in the nonlinear solver will get confused by that discontinuity, and chances are it won't converge around that. And there's too many things to actually change when you're playing around with your design, and so there's not really an optimal solution for this. It's really, what your gut feel and what the flux density is going to be based on your winding experience. We'll talk a little bit more about this in just a minute. Okay, I kind of tried to explain that here. I kind of stopped double-clicking that. Okay, by changing the flux density, you can minutely change the secondary output voltages. That's kind of what I'm talking about. You can use this. There's a method called Flux Fine, which will go and do this operation for you, and it finds the optimal flux density to minimize the error of both the the full load to your specified voltage that you want, as well as the voltage regulation. Okay, there's one last thing, is that the majority of transformers, these documents in here talk about this thing called, circular mils per amp, which is the diameter recommendation of the wire diameter per amp. And they do this for temperature rise. You don't want your transformer to run 100 degrees above above ambient, because your wires could get really warm and you could burn your transformer out. So they have a spec in here where most of these transformers will start 800 circular mils per amp. And what that does is it keeps your transformer cool, because the copper itself can dissipate the heat from the voltage loss. Having larger copper ends up taking more space in your bobbin, but it lowers the resistance. So there's a lot of trade-offs right there. And by changing this thing called circular mils per amp, you can opt to have better regulation, which is bigger wire, but then you'll need a bigger window, which means you might have to have bigger lamination. Or you can go smaller at the expense of having an increase in temperature rise. It's all, if you go in and play with this code, you can look at all those different kind of trade-offs, and it's really quite easy to do that here. Okay, and then the last one, we talk about the copper losses, and the copper loss has to deal with if you've got grain-oriented silicon steel or not, or non-oriented. Grain-oriented has less copper loss. Core loss. There's less core loss, and the core loss contributes to the temperature rise. All right, now, so you can go in and change the core loss percentage as well. Here are the default values. The default values for all these variables. These are variables that you can change. This is when you create your transformer class itself. This is the default values that get set. Core loss, efficiency, line frequency, stacking factor, the loss factor, the insulation thickness, which is like the insulation that you put between the individual windings. And I'm using 1 mil Kapton tape, which is 3 mils, and it has a 5,000 volt voltage isolation barrier or dielectric breakdown. And the wrapping thickness is what the overall outside of the wine's going to be. And then this white extra is the account for the bells and the brackets, and as well as the screws and stuff, because you're going to look at temperature rise. So you got to, you want to look at the weight of everything on the transformer itself. Insulation watt layers is how many layers of that Kapton tape I'm actually going to wind around. Theoretically, I can get by with just one, because that's 5,000 volt dielectric breakdown. But if there's a pinprick or whatever in there, you want to go ahead and do a couple of those just to make sure as a safety measure. All right. I'm going to stop here, and I'm going to pick this up, and we're going to start looking at this transformer right here. So this would be a good stopping point for you to go back and look at the Wolpert text and kind of review what I've been talking about before we actually get into looking at some examples. Okay, I'm back. Let's look at some examples here. The first one is a very simple example. This is the Python code that you're going to end up typing in. You define your primary and your secondary windings. You can have an array of those. You can have as many secondaries as you want. And we'll show an example, a more complete example for a Fender Deluxe down below here. But this is a simple transformer. It's for a 12.6 volt filament transformer at 3 amps. And so my primary voltage is 115 volts, and I specify down here this P is for primary, the S is for secondary, 12.6 is the voltage that I desire, and I want 3 amps out of this, and it's got a tap at 50%. Then I build my transformer object here, and I'm going to wind the primary on first, then I'm going to wind the secondary. I read that when you wind transformers, you want to put the small gauge wire on the bobbin first, because it has to make that sharp turn around the bobbin corner, and then you wind the heavier windings on second. And then I read something else that says don't do it that way, because if you have the fine gauge wire on first and you try to put the heavy gauge wire on after, you may end up crushing the fine gauge wire from the wire tension of the heavy gauge. I don't have enough experience in winding transformers to know which way to go, but you can definitely change that here by changing the order at which your windings are stuck into this array when you're instantiating the transformer class. You pick your flux density at 65,000. We just randomly chose that, and we tell the transformer class to, my transformer object to go ahead and compute itself, and then I'm going to go ahead and print a report. So I'll go ahead and start my code here. I'm going to execute that. That's going to do a bunch of imports. And then what I'll do is I'll calculate this. So you see that it's very fast. It's already done. And so it's gone through, and here is the wire selection that it's going to choose from. And there's a couple of extra files in the directory, the source directory. It's the wire gauge file, as well as the lamination file. I'll go ahead and show you those. Let me see here. We'll go over and look at the wire gauge file. It's a CSV file. And so the CSV file has got this. I got this table from I probably got it from the Wolpert book, and I typed it all in here. And there's a column over here at the end called have. These are the gauges that I actually have. Okay, we'll talk about why we want to use that in a minute. But for now, it's going to pick the optimal choice of wire gauges initially. So these are the wire gauges that it knows about. It's going to pick from those. So based on our calculations up here, these are the requirements that come over. And here's the transformer. The design process starts here. The design values come out. Here's the computed VA is the 37.8 VA. The flux density is 65,000, which equates to 10 kilogauss. Circular mils per amp is 800. That's the default value. And here shows you the temperature rise here. It's going to be 23 degrees. And then down here it tells us the lamination size, so the stack height is going to be, and the stacking factor, and the core area, and the effective area, and the window height, the window length, all those kind of things are here. The windings here, it has the primary listed here, and the secondary here. And down at the bottom here, you can see the voltage outputs. So with this initial design, our voltage output is going to be 12.54 volts. And our open circuit no load voltage is going to be 13.56. That gives us a regulation of about 8%. Okay. And here's our bobbin. This is how the bobbin is going to stack up. And it says, okay, here's the bobbin base. There's going to be 11 layers, 721 turns, and of 25 gauge wire. And it tells us the heights and that kind of thing as the stack is getting built up. And we get all the way to the end, and we find out that our stack height is 0.52 inches, but our stack window is 0.5, so we're a little bit over. So this isn't going to be able to be windable. Now, what are we going to do? We have a lot of different choices here. The first one we have is, let me see here. I got to look at my notes. Hold on just a minute. Okay, the first one is we can have the transformer class print out the flux table. All right. Because this number here, let's talk about the flux, changing the flux density. If we decrease the flux density, well, let's look at the equation for flux density. It's up here. Number of turns here is the voltage. This is the constant. This is our primary voltage, and we have this constant here. The B is our flux density. A is effective area. With this lamination, we are, this value is fixed as well as the frequency is fixed. So by changing the flux density, we can change the number of turns on the primary, which equates to changing the number of turns on the secondary. So if we want to decrease how many turns we put on there, we have to increase the flux density. We can do that down here by, we can change this. Let's say we want to change this to 70. And then what ends up happening to our build height, okay, so now we're at 99. I typed in some extra code here. This thing prints up the flux table. This will scan through the flux range and actually show you the build heights as well as the errors involved. So if we run this, we come down here, and underneath this, this scans from 50,000 flux density up to 102, which equates to 15.8 kilogauss. And if you look at this, you can see that Flow flux density requires more turns, which fills our bobbin. So up here, our percentage is really high. So we cannot do that at this. This is 125%. So our bobbin's really big. It won't fit in the window. We can come down here and look at this range. Okay, and you can kind of see that it's continuing going down because as the flux density goes up, the turns ratio goes down. The number of turns goes down, so our bobbin gets smaller and smaller. And you can see that the air is going down as well because we have less copper involved, so we have less loss, and you can see that these values are running around. So like if we just want to pick, let's say we pick 88,000, which is right about here, that's going to leave us at 12.7. Or we could let's pick 89,000 will be it, or this one here. Let's pick 90,000 as a flux density. And then we'll see what ends up happening. Okay, so our fill window now went down to 81%, so we're looking pretty good. Wolpert talks about if the fill is more than 85%, you should be very cautious. That's based on how well you do your wind. If you're not very careful doing your wind, you'll never get the thing to get back together if it's above 85%. I'm not familiar enough with how my winding machine is going to work and my technique, so I'm going to have to be very cautious when I choose the fill height. But you can see up here that our voltage turned out to be 12.58, which is the final voltage. Okay. There's a couple of other things we could actually change. Well, the big thing is here, if we look at this is 25 gauge wire for the primary, and the secondary wiring in is 16 gauge. All right, I know that I don't have those two wires. And I'm not going to go out and buy X number of feet, which it tells me how many feet I need of this wire. I don't want all these gauges of wire hanging around because I'm not a transformer manufacturer, so I don't have all this thing. It's going to be expensive. When you buy magnet wire, you got to buy by the pound, and it gets expensive when you do it that way. So this software has a provision for only choosing wire gauges that I have, and this last parameter in the transformer instantiator is called have. If you make have equal to 1, it's only going to pick from the wire gauges that I have. Okay, and you can see down here that in the requirements, it's forced to pick from these wire gauges. And you can see down below here, when it was forced to do that, what ended up happening was it picked 24 gauge wire, which is bigger, and 15 gauge wire, which is bigger. And now our fill window went up to 92%. Okay. So now what do we do? We can go in and change that circular mils per amp, which will force us to pick smaller gauge wire, which results in a higher temperature of the temperature change. You see right now the temperature rise is 15 degrees C. But let's say I want to change my circular mils down to 600 from 800. Let's see what the temperature rise is going to effectively be. It's still at 15. That's because it didn't change the gauges at all. So I'm kind of stuck right here I can change the flux density. Let's go look at that. Let's go look at this table again. And you'll see that the fill goes down to 88. So if I made the flux density 100,000, it would go to 88%. All right. The other option I have is I can change, if we go back up and look at this equation for the turns ratio, this one right here, I can change the effective area. The effective area is the stack height of the core times the width. When I bought my E100 from Edcore, I was able to. I ended up getting two types of bobbins. I got the 45 VA bobbin, which is a square 1x1, and I also got the 50 VA bobbin, which I think is a 1 1/4. So I can change the VA here, which will increase the area, which will make the turns ratio better. So what happens if I make a bigger transformer with the same lamination? All right, I come down here. We see now that my fill window is back down to 84%. All right, and my V out is at 12.5. So now I got to go down and look, and I can find one of these values that's close to 6. This is close to 12.6, but I need the build to be, in the 80s, below 84. So it's like almost any of these down here will be good. Now I know that laminations that I ended up getting can take higher flux densities. And let's just pick one down here that's pretty close to what we really want, which is going to be, let's say we want to pick this one right here, 87. We want our flux density to be 87,000. So we change 90,000 to 87. We rerun our numbers, and we see that V out is now equal to 12.6. Okay. So you can kind of see that how easy it is to actually change the circular mils per amp, the flux density, the VA itself, and the calculations are very fast. There's one additional function here that is actually called Flux Find, which I talked about, and you can put in Flux Find right here, and it will find the optimal choice of flux density for this particular design. And if you go down and you look, and it actually turns out that it picked 87,000. We'll see why this is more important on this next example. All right, let's go down and look at the, there's a bunch of additional transformers down here, this part of this code. Oh, we've got to do one more thing here. We got to look at, we have to look at, we have to do some plotting here. Let's put a cell in below this thing. We'll do a cell below. And then we're going to plot the wind itself. So we would do a plot of winding 0. And this is going to show you what the plot looks like when the machine code is going to get run. And you can see that here's our window length. It looks like it's 1.3. And it's going to go across here, and it's going to end up at 60. And it's going to go back and forward and back and forward. So this is what the primary winding is going to look like. Secondary winding is going to be winding number 1, which is here, and it's tapped now. So this thing is going to tell you that the machine needs to stop here, so you can do your prep work for the tap that's going to happen 10 turns later, and it's going to put a tap right there. All right, so this is a this just kind of shows you what the machine is going to do. And then there's one last thing. If you actually want to look at the G-code itself that's going to get sent to the machine, you can look at the G-code by having it, you can print the G-code out here. And it's going to give you the build table that you can actually just take this and run this right into your right into your CNC machine, if you got it set up correctly. Okay, the machine class that I ran in the last demonstration actually takes all the stuff and it loads it all into the machine, and then you can wind it from there. You can look at that example in this previous video in the Valve Studio from a couple of days ago. Let's look at a real example down here at the bottom. The real example is this one right here. This is for a Fender Deluxe. This is off the 5E3 design. It's got a preamp of a 12AY7 and a phase inverter using a 12AX7 and two 6V6s, and it uses a 5Y3 rectifier tube. So this example is going to show you that this is multiple secondaries. This is also, I threw in fixed biasing for this, and so I have a tap. I have actually a winding to generate the negative voltage for the negative grid voltages. So this thing actually has 4 secondaries, and you can kind of see them laid out here. And I specify that I want the filament voltage to be 5 volts at 2 amps, and I want the 6.3 filament winding to be 1.7 amps, and I want a tap at 50% for that. I want the secondary for the high voltage to be at 325 volts, and it's got a 50% tap at 125 milliamps. And my secondary is at 20 volts. This is going to be the one that generates the minus supply. And it's going to be, there's no current flow going into these grids, and so I only specify that I want 2 milliamps out of that. Okay, let's run this one. All right, so you can see that the initial flux density I chose was 75,000. And if we go down, we can see that, I picked a 90 kV, 90 VA lamination for this. Here's the requirements for the thing. I'm going to go ahead and use the wires that I have. And we can see that this works out to be a 61 VA transformer. At 75,000, the flux density of 75,000, that's 1.7 kilogauss. All right, the temperature rise is 16. We can kind of see down here our windings. I ended up putting the windings in order of wire gauge, so the heavy gauge wire is actually on the bobbin first. So in this case, you can see that this table is actually shows you how it's actually going to get wound. That has to deal with how you actually created this array that gets passed into the initiator or the constructor for your transformer class. So what we end up having down here is we have 18 gauge wire on these two filament. The primary is at 22 gauge, and the secondary, the high voltage secondary, is 27, and the bias, the screen winding is 40 gauge, which is very small. You can see that there's a number of layers here, and here's a turns ratio. Turns ratio on this one is there's almost 1,200 turns on the high voltage secondary. Here are the voltage outputs that we're going to get. We're going to get 4.7 and 6.37. This is pretty good for the filament voltages. 324.86. So this design actually worked pretty well at 75. The flux density of 75K, and our window fill is 83. All right. Well, can we do any better than this? If we look at the flux table down here, this is printing out a bunch of errors. This is printing out the error itself right here. So this is the error. This last column is the error. The error for the full load voltages versus what I desired, and the regulation itself. So this is where the Flux Fine function actually comes in really handy, is the fact that it does a better job of finding the optimal flux density than me just poking around and guessing what it should be. So I'm going to have it max out at 100,000 lines. So if we run this here, you can see it runs pretty fast. Now what are our output voltages that we get here? We get 5.0, 6.3. It's very close. This thing found the flux density to be 90,000. And by increasing the flux density, the number of turns decreased, and so our fill window is a little bit smaller, which would be good because there's so many taps coming out of this. We're going to have a lot of wires coming out. And the other thing is our temperature rise went up just a little bit. Or probably went down, actually, because there's less wire in there. Okay, let's look at the, get down to the bottom here. Let's look at one of these taps. Let's look at the wind itself. This is wind number 1, which is the 6.3 volt wind. You can see it's got a tap right in the center. It's going to wind this all the way across. And so here's the real question. What would happen? Can I make this design, this only is 61 VA, can I make this design fit in a 65 VA lamination, which is a little bit less expensive? Okay, so let's run this again. All right, at 65 VA, you can see that our fill window, we're up to 92% on our fill. So we went down in lamination size, but now our fill's really, it's too much. So what can we do? We can change the flux density, but we already found the maximum flux density. It is at 99,000. We can change it even more, but we're getting up there now. We're at 15 kilogauss. And the other thing we can change is the circular mils per amp. Remember, that deals with how big the wire gauge is going to be. And I think let me see if I change that, what does that end up being? I'm going to change it down to 650 from 800. That's the default value. So it's going to run all the numbers again, and it looks like it went down because it got to choose smaller gauge wire for the wire that I have. So now my fill window is now 84%, and the temperature rise went up to 19C, which is completely acceptable. Wolpert talks about making sure that your temperature rise above ambient does not result in a combined temperature of 105C. You're going to run into some problems if that thing gets to be 200 degrees. One, it's going to be kind of dangerous, and two, you may have problems with your insulation melting, which would not be good. Okay, but I have this high voltage, high temperature capped on tape that I'm using, so I probably won't have a problem there. But 19C is pretty good. That's going to be 19C above ambient, which is 23, so that's about 43, which would be about 130 degrees Fahrenheit. Okay, so let's look at our winding number 4 is that the high voltage winding. This is the one that's got the 1100 winds on it. That's not right. Winding number 3. Well, let me type this correctly here. This has got, okay, so here we go. This is the high voltage wire. It's winding number 3. So you can see we go along here, and then this is our, we're gonna stop here for the tape, and then we're gonna stop 10 turns later for the tap. And so this is just a visual representation of what's actually going to happen. One last thing here, I'm going to show you one more additional thing that this will do. If you look at this winding stack, it tells you here that this layer is a partial layer. So it's going to do a complete fill of the wind. It's not going to wind the wires right close together. It's going to skew them so that the complete wind is all the way across and fills the window. So this says a 47% full if it was winding tight, and 58% if this one's full. So if these two were added together were less than 100, we could do both of those windings in the same layer. And we can see this if let's just plot one of those things. Let's just plot that number 0. So you can see that what's going on is it's starting at 0 and it's working all the way across the bobbin, and it's going to end up at 16 turns. We can tell the G-code to not do that by, if we come up here and in the winding, when we define this winding, if we say fill equals 0, and we run this again, we can tell it to not do that, so that when we plot this, it will smash all the wires together, and then we may be able to get 2 windings in the same layer on the bobbin by setting the fill on the winding when we define it to not do this fill. Okay, I hope that makes sense. This particular case, these two numbers are more than 100%, so it's not going to work out. But we could monkey with this a little bit more and get all that to work, but we don't need to because our fill is 84%. So what I'm going to do is, from this point on, I'm going to wind some power transformers for this power supply that I'm working on for my bench. We'll go ahead and verify that a lot of this design procedure actually works. And then after that, I'm going to take this same thing, and these All these equations work at 60 hertz, and so we're not too concerned about leakage inductance. At this point, we could calculate all that stuff, but we don't need to. I think that's taken into account in this efficiency number that Wolpert sets at 1.11. When we design audio transformers, we have a bandwidth that we want to look at, and so we have to be very cognizant of the leakage inductance and the capacitance itself. And so we can't use the same procedure for doing audio transformers. We have to have a different one for that. Luckily, Wolpert has an audio transformer book as well. I'm going through that, and I'm going to modify this. I'm going to make it separate. I'm going to copy this and start again with one that's to winding audio transformers. And we'll go through that, and we'll be able to wind up our audio transformers and be able to predict performance. We'll wind up some of those, and then we will actually measure the bandwidth on the bench here. Okay, thanks for watching. I know this has been pretty long. I hope you get something out of it, and I hope that you actually go in and play with this tool. You can clone the GitHub repository and run this right out of Jupyter Notebook right away without having to do much install beyond Python itself. And it allows you to create your designs and iterate very quickly on the flexibility that you have in terms of choosing your flux density, your circular mils per amp, your the wires that you have choice from, the cores that you have. There's a lot of different things that all are involved in your decision. Whether or not you buy lamination, you get some specs for the flux density that it supports. You find something, you tear apart something from salvage, whatever. You should be able to use this tool and figure out your turns ratio. And if you're going to build your own coil winder, this thing is going to send the right codes over to Gerbil. All right, thanks for watching. This is the Valve Studio for January 30th, 2017.